Okay, so what I wanted to do, I told you I would do the other homework problems, so I will do that. And then we will do one more from the notes. And then we are moving on to bigger and better things. So here we go. I think I did see it. I did B, right? Yeah. All right, so I'm going to do A now, and this is on the homework. So the problem is, or the equation is this. And I'm going to do it all the symmetries. Okay? So again, you do not have to memorize the tests, but you have to be able to use them. So for x-axis, there's always two options. For all these, there's two options. And when you, one or the other might work. So you have to try them both. If the first one comes out no, that doesn't mean it's a no for sure. You have to try the second one. If it comes out no, then it is a no. All right? So here we go. So we're going to replace with r negative theta. So 1 plus 2 cosine negative theta. So what do you remember about cosine of a negative? It drops off. So this is the same as this, which is the same as the original. So that's a yes. That's a yes. Now, if it's a yes, obviously it's a yes, and you don't have to try the other one. All right, y-axis. First one, I'm putting in a negative r and a negative theta. That's the first test for y-axis symmetry. Well, I think you can see this one's going to be a no because we just said that negative goes away. So is that equation the same as the original one? No. So we'll try the other one. So the other test, is r equals 1 plus 2 cosine. Now I'm going to take out the theta and replace it with pi minus theta. How do we do cosine angle minus angle? How do we handle that? Karen's getting out her formula sheet because she doesn't have it memorized. They didn't ask you to memorize it. That one's going to be cosine pi. No, cosine pi, cosine theta, plus sine pi, sine theta. Right off your sheet. All right, now pi. Pi is over here, right? On the circle, in a circle. And we know cosine is x and sine is y. So we'll just plug them in. So cosine pi is -1. Sine pi is 0. So what do we end up with? R equals 1 plus 2. All right, what do we got here? Negative cosine plus 0. So R equals 1 minus 2 cosine. Is that the same as the original equation? Nope. So guess what? The y-axis, there's no symmetry about the y-axis for that equation. If you graphed that Lima sign, it's not symmetric about the y-axis. It is symmetric about the x-axis. All right, and finally, the origin. All right, so to do the origin, our first replacement is -r. All right, is that the same as the original? There's no simplifying to do there. Is that the same as the original? No. So then we're gonna do the second one, which is r equals 1 plus 2 cosine theta plus pi. Is that kind of like the one we just did? Alright, so this one's going to be 1 plus 2. Alright, cosine theta, cosine pi, minus sine theta, sine pi. So again, cosine pi is -1, sine pi is 0. So isn't this just going to be negative cosine again? I think that's a big no also. I want you to think about, what's the lima sign look like? Dented in circle, a lima bean, a heart, right? That kind of shape. So think about when you graph those things. And I'm a horrible artist, I'm absolutely horrible. But didn't they look something like this? Weren't they situated, or they could be up and down, or it could be something like this, right? Does it make sense to you that the lima sign, this lima sign, would be symmetric about one axis but not the other? Look at this picture. Isn't this one symmetric about the x-axis? This one is symmetric about the y-axis, but that shape really isn't going to be symmetric about both of them. And how about the origin? Does the picture, the shape kind of tell you, hey, there's not going to be any symmetry to the origin for that shape, right? Whereas if you had a lemniscate equation, what's the shape of a lemniscate? A figure 8, an infinity symbol. So what about that guy? He has symmetry to the y-axis and the x-axis and the origin. Yeah. Okay. All right, so that's that. I'll do one more. Let's do problem A from the notes. This is the one I started, but I didn't read the directions, so I didn't do it right. So this is problem 9A in the notes. And I'm not doing all of them. It says, is it symmetric about the y-axis? So r equals 3 minus 3 sine, another lemniscate. Is it symmetric about the y-axis? So first test, change r, change theta. That's the first test for the y-axis. Now, this is a sine. So what happens to that guy right there? He comes out here. So negative r equals 3 plus 3 sine. Is that okay? When you divide, you're going to get negative 3 minus 3 sine, which is not the same as the original equation. All right, now let's do the other one. You can't make a determination until you do the other one. So r equals 3 minus 3 sine pi minus 3. All right, so let's figure out all this stuff. So what's the sine formula for a difference? Sine of the first, cosine of the second, minus cosine of the first, sine of the second. And it's pi again. So So sine pi is 0, and cosine pi is -1. So r equals 3 minus 3 times what? What's left in here?
Positive sine.
Actually, just positive sine theta, that's all that's left inside that bracket. So r equals 3 minus 3 sine. Is that matching the original? Yeah. So there is a beautiful example of the first test didn't work, second one did, so it does have symmetry. All right, I've already asked you to have that be working on that 6-5 homework. I have done 2 of the problems for you. We're gonna go through a little bit more of this before lunch, and then if you have questions about something else on that, we can do it. But right now, we're going to do the last section of the chapter, which is a section that you are gonna find absolutely fascinating. We have Mathley, Pide, and de Moivre's theorem all coming together at the same time. It is so exciting. All right. So number 1, 6.6, number 1 says plot this complex number. Now, we can name complex numbers, and the standard notation is with the letter Z and a subscript. So this is our first complex number, Z sub 1. 1 plus 3i. Now you know what a complex number is. A plus bi. There it is. Now how do we graph it? Well, when we graph in the complex plane, this is the real axis and this is the imaginary axis. Each complex number has 2 components, a real part and an imaginary part. So we're going to go over 1, up 3, and make the vector that goes over 1, up 3. That's how we graph that number in the complex plane. It's very simple. X, Y. Okay. This notation is the modulus of the complex number. But tell me what that notation means in vector land. The magnitude. So this, I just drew a vector. If it's a vector, it has magnitude. What's the magnitude of that vector? Square root of 10. Square root of 10. Kids, right triangle over 1 up 3, square root of 10. Trigonometric or polar form of a complex number. So, we have looked at polar coordinates. So, rectangular coordinates are x comma y. You know that, you've used those your whole life. We've talked about polar coordinates. What are they? R comma theta, right? This is graphed in a rectangular system like this. This is graphed in a circular system. Complex numbers, okay, these are coordinates, ordered tables. Complex numbers can also appear in both forms. So this guy right here, x plus yi, is the complex form or the rectangular form of that number. This is called the complex or rectangular form. In polar form, that same number, let's see if we can figure that out without looking at our notes. Let's see if you can figure this out. What do we know about x? X equals r cosine theta. So this is r cosine theta plus r sine theta I. Both of these have an r in them, so I'm going to factor the r out. And just so there's no confusion with the variable, I'm gonna move the I to the front of this. And this is called the polar form of a complex number. So, in coordinates ordered pairs, we can either have x and y or r and theta. With actual numbers, we can have either an x and a y or an r and a theta. And how we switch back and forth is exactly the same. These get cumbersome to write over and over and over again. We're gonna have some problems where your answer might be 5 or 6 of these. So there's a shorthand version of that. You are allowed to write your polar form numbers using this notation, cosine, I, sine. Or you can always write them out longhand, whatever you're comfortable with. But this is kind of the abbreviated polar form of a number. So again, complex or rectangular form, Cartesian form, polar form. Convert the following to polar form. So we have the number -2 plus 5i, which if we graphed it, would look like this. Would everybody agree? -2 plus 5i would look like that. X, this is rectangular, Cartesian, x and y, x and y. We need to make it look like that. We need an r and a theta. Well, guys, with your eyes closed, you can find r. What's r? Root 29. R is the magnitude. That's r right there. Now this is theta. Theta must be in standard position. And make a little note, in polar form, theta has to be between 0 and 360. Polar coordinates, we got away with negative thetas, not in polar form, gotta be positive. Between 0 and 360, or 0 and 2 pi. All right, so what's my theta between 0 and, doesn't tell me whether you use degrees or radians, so we'll do this one in degrees, we'll do the next one in radians. My r is root 29. What's my angle? How am I going to figure that out? I'll do it in degrees. How am I going to figure it out? So second tangent, 5/2, 68.2 right here. Second tangent, 5/2. And then subtract that from 180. Did you get 111.80? This is the longhand form. This is like the official form. You are allowed to write root 29 CIS 111.80. Either one of those is perfectly fine. That's the polar form of that number.
Why do we have to use the degree if we know it's just cosine of 111 is just going to be 2 over 329? Oh wait, never mind. That was
You would be going back to this. Yeah, that would be back to that. All right, let's do the next one. We'll do this one in radians. -3 minus 4i. We'll do this one in radians just so we're getting some practice. We're changing it into polar form. Okay? Which means you need an R and a theta. I like to draw pictures of these. You certainly don't have to, but I think it helps. What's my R? 5. going to be my theta this time? Remember, standard position in radians, so I'm changing my calculator. Second tangent, 4/3. And then what? Plus 5. I got 4.07. Easy? That's exactly what we did a couple days ago. A couple days ago, we had points, and we changed them into points. It's exactly the same thing. It's just a matter of what your number looks like when you start, and that will determine what it looks like when you end. If it's an ordered pair, it's going to end up as an ordered pair. If it's a complex number with an I, it's going to end up as a complex number with an I. But the R and the theta are exactly the same. All right, number 4 says go the opposite direction. So our number is 3CIS 100, and we want that to be in rectangular, complex, or Cartesian form. Those words are interchangeable, which means x plus yi. If you want rectangular, Cartesian, you gotta have an x and you gotta have a y. That's what you're looking for. All right? 100 is not special. I'm gonna need a calculator. I can't do this one exactly. How do I find x? Oh, you already told me. Somebody already did today. What's that? R cosine theta. So I'm going to set my calculator in degrees, and 3 cosine 100, negative 0.52, 3 sine 100, plus 2.95 I. There it is. There's the number. That's all there is to it. X is always R cosine theta, and y is always r sine theta. Okay, super simple. All right, what about B? Same thing, only our calculator has to be in radians. You gotta pay attention to that. It's kind of a pain in the butt, but you gotta pay attention to it. So 4 cosine pi divided by 7. For that one, I'm getting 3.6. 4 sine pi divided by 7 plus 1.74i. The I always goes with the y. It's x plus yi.
The negative answer?
Yeah,
Okay,
yep, whatever theta is, yep, it's gonna be in standard position.
Okay.
Now, pi over 7 is in quadrant 1, that's
Yeah.
why both of those came out positive.
But like
So this
if-
would be the same.
Yeah.
Yeah, because 100's in quadrant 2. All right, everybody okay with that? Easy peasy. All right, now number 5, no calculator. You're going to do exactly the same exercises, but we're not going to use a calculator. We can get away with that because look at the numbers in the problem, you guys. When I draw that over 1 up root 3, I should recognize that angle. 60, if I'm in degrees, it doesn't really say. Okay? So what is my polar form for this number? What's my R? 2. What's my angle, my actual angle? 120. Done. That's it, you guys. What would my angle be if I were in radians? Pi minus pi over 3, so 2 pi over 3? It doesn't say, so either one is fine. All right, now, other way around. Convert to complex form. So you have polar, and we want to change this to complex. Complex rectangular Cartesian means find x and y. Okay? So, how do I find x again? 5 cosine 210, 7 pi over 6, which is 210 degrees. And y is going to be 5 sine 210. So I'm going to find 210 degrees, or 7 pi over 6 radians, if you like to look in radians. That will be right over here. The reference angle is 30. Everybody keeping up with me? So, what's the cosine? I need the cosine right here. What's the cosine? Negative 3/2.
I had no clue that we had this.
And what's the sine?
I didn't know we had this.
Negative 1/2. So negative 5√3/2. Remember, this is just 5/1 times that fraction. Minus 5/2 I. Remember, the I always goes with the Y. Tess?
How's the radius 5?
Huh?
How's the radius 5?
It's right there in the problem. I'm just using my triangle to find the cosine. Okay, this is just a picture to help me find that. This is not a picture of that number. This is a picture of that angle. So it's giving me the cosine and sine, which then I have to times by 5. Now, if you want to blow this up and multiply by 5/2, what do you mean by 5/2? Then you'll have an actual picture of that number. But I don't need to do that, I can just do this. All right, so when you get back, we're going to start the fun stuff. So I want you back at 50, in your seats. In your seats at 50. You hear from her?
Huh?
Have you heard from her yet?